All right, so here we have lesson 4, a simulating conversation, simulating simple experiments. Okay. Learning goals in this lesson are to conduct trials using a simulation to determine probability, conduct a large number of trials, and observe the long-run relative frequency of outcomes to demonstrate that experimental probability approaches theoretical probability. The larger the sample size, the better it is. Just like in science, the more trials you have, the better it is, the more reliable it is. Key terms: simulation and random number table. Okay. So here we have conducting probability experiments are helpful when you are rolling a number cube, flipping a coin, spinning a spinner, etc. What about more complicated experiments? How can you use models to run simulations of experiments when it's not possible to do the experiments in real life? Our warm-up for today: solve each proportion. Well, I know when I have a proportion, I can scale up or scale down. So if I look here, 1 to 3 is times 3. 24 times 3 would give me my answer of 72. I could take 3 times 24. 3 times 24 is going to be 72. Divide it by 1, and it's going to be 72. So x equals 72. 10 times 9 is 90. 90 divided by 4 is going to be 90 divided by 4, 22 and a half. 22.5. Okay. 3 times 212. And then I divide that by 3. I'm sorry. Then I divide that by 5. And so P would be equal to 1, 2, 7, and 3/5. As writing these as decimals, this would be 22.5. This one would be 127.6. Okay. And so cross multiply. So I do the ones I know, divide by the other, do the ones I know, divide by the other, do the ones I know, divide by the other. Sometimes I can scale up or scale down, kind of like equivalent fractions, to find the answer that way. Okay, getting started. Designing sims. Design a spinner that could be used to generate the experimental probability of guessing the correct answer on a true or false question test. Explain your design. Okay. Well, true, false. There are only 2 options, and they both have the same probability. Okay. Design a spinner that could be used to generate the experimental probability of guessing the correct answer on a multiple choice test where each question has 3 possible answers. All right. Sorry, my sister's dog is all sorts of upset today. There are 3 options that each have the same chance of occurring. Okay. And then we have design a spinner that could be used to generate the experimental probability of guessing the correct answer on a multiple choice test, where each question has 4 answers. Explain your design. All right. Well, it'd be kind of the same thing. We would have, well, let's see here, A, B, C, D. And then there are 4 options that each have the same chance of occurring if you guessed. Now I want to go back here, and if I think about it, let's say true is correct. So I have a 1 out of 2 chance of being right. Let's say 3 is right. If I'm guessing, I have a 1 out of 3 chance of being correct. Let's say C is correct. I have a 1 out of 4 chance of being correct. So if I'm guessing, I want there to be less choices because I have a higher probability of getting the right answer. Probability goes down as there are more choices, which is something I've learned from Edulastic. If I add another option, there's more people that are wrong on it. Okay. All right, activity 4.1, simulating baby births. What % of babies born at a certain hospital are girls? One way to answer the question is to perform a simulation. A simulation is an experiment that models a real-life situation. When conducting a simulation, you must choose a model that has the same probability of the event. What model might be appropriate for creating a simulation of this event? I could think of maybe like tossing a coin, or like on the last page, a spinner with 2 sections. Describe the sample space for this situation. Well, the sample space would be, you would either get a girl as your choice or you would get a boy as your choice. What is the event you are trying to determine? The % of babies born at a hospital that are girls. Just took that from the question right up there. Okay. Suppose the probability of a family having a girl is 1/2. What % of babies born at a hospital would you expect to be girls? 50%. Okay. Let's use the toss of a coin as a model. Heads will represent the birth of a girl, and tails will represent the birth of a boy. If you toss a coin twice, list all the possible outcomes from this simulation. So if I tossed it twice, I could get 2 heads, 2 girls. If I tossed it twice, I could first get a head and then I could get a tails. 1 girl, 1 boy. If I tossed a coin twice, the first one could be a boy, the second one could be a girl. If I tossed a coin twice, I could get 2 tails, and that would be the same as having 2 boys. Okay? And so those are my options if I toss a coin 2 times. All right, so now we're going to do the simulation, and we're going to start with just tossing your coin 2 times, and I have the random coin flip here, and so I'm going to flip the coins, hopefully. And I get 2 tails and 0 out of 2. And so according to your simulation, was the experimental probability of a baby girl being born 0%? Share your results with your classmates, then create a dot plot for all the experimental probabilities. Did everyone end up with the same results as the theoretical probability of a girl being born? Okay, so if we do a dot plot of the whole class, so we would have 0 for my first group. Then I go around the classroom and I'm gonna move 2 heads, so that's 100% girls. Then a girl and a boy. A boy and a girl. I'm sorry, boy and a girl, and a girl and a boy. And then that is 2 girls. A boy and a girl. Just like me. 1, 2, 3, 4, 5, 6, 7. About 30 people in class, so there should be, well, at the end there we're doing, that was 2 girls. I'm sorry, 2 boys, 2 girls. A boy and a girl. 4, 5, 6, 7, 8, 9, 10. 2 girls, 11. 2 boys, 12. Boy and a girl, 13. 14. 15. All right. Share your results with your classmates, then create a dot plot of all the experimental probabilities. Did everyone end up with the same results as the theoretical probability of a girl being born? No. In fact, it was 1, 2, 3, 4, 5, 6, 7 that did, and then 4 and 4 and 8. Half did, half didn't. Half did, and half didn't. Okay. So now they're going to start increasing the amount of coins tossed that we get. All right. And so now if we look at this and we're going to flip the coin 8 times, and then I'm going to flip the coins. Oh, what? That seems impossible. It's done it twice in a row today. I'm not happy with this. I'm going to use a different one for the next. I'm going to use a different simulator for the next one. All right. So 1, 2, 3, 4. So this is like 8 out of 8. And so according to my simulation, the experiment now it's 100% chance of being a girl. All right. Now I'm going to 4, 5, 6, 8. All right. Now I'm going to flip for the class again. I'm going to put this on there. And so now we have 1, 2, 3. So that's 3 out of 8, which would be right there. Oh, first of all, mine was 100%, so that's 2 groups. Then 3, 4. That's 3 groups. That's 4 groups. Five. That's 5 groups. 1, 2, 3, 4, 5. That's 6 groups. 7 groups, 8 groups, 9 groups, 10 groups, 11 groups, 12 groups, 13 groups, 14 groups, and last but not least, 15 groups. Okay, so how do these results compare to from question 6? Well, if I look at 6 here, it was kind of like it was pretty spread out. Half of them were in the middle, and then the others were all kind of spread out from there. This one feels like it's like this is like there's like 3 main sections here. There's 0, all, or in the middle. Okay. Now this one feels more like a normal curve to the data. There's a nice shape. There's a nice distribution to the data, which we'll talk about later this year still. And so this one has a nice even distribution. And so it's most of them are in the middle. So like that one has 7 in the middle for the first one we did. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 were right around the middle here. So I would say these are closer to the middle. More of my fictitious groups had results that were closer to the middle. So the results should be getting closer to 1/2, and it looks like they kind of are with those first 2. And so now I'm going to get a different flipping coin option that'll work better, and we'll go and up them up again. We'll do some more trials again. All right, so now we're increasing our sample size again, and so now we're conducting 50 trials of the simulation. We're recording the results in the table using tally marks. I'm not going to use tally marks because I'm going to use this right here. And so if I go and I flip this, oh no, it's going to think for me. And then it gives me the stats. And so 31 and 19. And so 31 heads. And then 19 tails. This is going to be 62% are girls. And then this is going to be 38% are boys. And so we're going to create our dot plot of the possibilities. And so girls are 62. And so if I'm thinking about this is 75, this is 50, this is 25, this is 0, this is 100. Let's see here. 62. So this is about 62.5. And so that is where I'm going to put that first one right there. Okay. All right. So 62. Then I'm going to start doing this for the other groups then as well. And I'm going to flip it again. And then this is 27 is heads, and so that's 54%. I'm multiplying it by 2 each time. 54% is going to be pretty close to here. Then I'm going to flip it again, and then that's going to be 29 times. That's going to be times 2 is going to be 58. So that's going to be right about there. And then 23 is 46. So that's going to be right about there. And what I'm noticing initially, 23 is going to be 46. It's going to be right about there. What I'm noticing is that this is harder to make a dot plot with, so it might be a little off. 46, which is right about there. 52, which is right about there. The second thing I'm noticing is that a lot of these are closer together, 48, and right in towards the middle. And 22 times, which is 44. So it seems like the more trials we do, the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The more trials we do, the closer we get to the middle, the closer we get to the theoretical probability. And like all of these are really close compared to what we had before. All right. Almost all the groups are near 50%. What was this? This was like 44% was the least. And then I had the most at 62% actually. And so everything was between that. Whereas before we had a whole bunch that were further apart. So we kind of start where it's pretty separate. Then we get so it's getting closer towards the middle. And then as we increase the amount of trials, we get a lot closer towards the middle. So what can we conclude about the experimental probability of an event and its theoretical probability as the number of trials of the simulation increases? That's my sister's dog. As the number of trials, he's not going to stop. As the number of trials of the simulation increase, the experimental probability gets closer to the theoretical probability. And so that's kind of like when they take surveys, they try to take so many to get closer to the actual answer. That's why in science we do so many trials to get close to the actual answer. All right. And so the larger the sample size, the higher the probability that is what is going to occurs. It's not always true, but using simulations to generate experimental probabilities is very useful in estimating the probability of an event for which the theoretical probability is difficult or impossible to calculate. As you have investigated, the experimental probability of an event approaches the theoretical probability when the number of trials increases. Okay? And so that is the end of lesson 4.1.